welcome. Yes, so there seem to be probably high expectations because the talk was mentioned several times. But actually, in this first lecture, I will not yet talk about the security proof. It will rather be about what I call the foundations of security. Before some of the things that were mentioned before will pop up again. But I would like to very briefly start by connecting it to the very nice start that Uli Maurer did when he started the lecture on why do we do that? Why should we care about quantum cryptography? And of course, one reason is that it's fun to do it. I think I wouldn't do this job if it wasn't fun. Do something else. But there are other things that are also fun, so that's not the explanation. We could also hike up a mountain now, and I'm sure Ramona would agree that this would also be fun. But there is something else to it. So what is this additional, or maybe the core thing we want to do when we do cryptography? And I have to say I'm actually more modest than Uli. Uli is an engineer, and generally engineers, they want to change the world. Now, my goal is merely to understand the world. And this is usually probably the difference between engineering and physics. So, for example, we first had to understand that the moon is actually some sphere on which we can land, and then the engineers could build rockets and fly there and actually do something that, in a sense, changed the world. So it's about understanding things. And what are things? I would say understanding cryptography goes very far. It forces us to understand large parts of how the world works on a fundamental level. And what I mean by that, I would like to illustrate briefly. And I think this already connects to things you have heard also in Norbert's lecture. So in a QKD protocol, you have, of course, parties Alice and Bob, for example. And actually, in the protocol that Norbert presented is a prepare and measure protocol. These are the protocols invented by Gilles Brassard and Charlie Bennett, for example, BB84. But he also mentioned there are entanglement-based protocols invented by Arthur Eckert. And I would like to briefly mention them because, in a sense, they are even more striking in what they achieve. So there, the way you think about, or you can think about them, is that you have an adversary Eve, and the adversary Eve basically sends information to Alice and Bob. So Alice and Bob later may also communicate classically, but so this could be classical communication. I should write here classical, but there is quantum communication only from Eve to Alice and Bob, but not in between Alice and Bob. Which means Eve, this makes it even more explicit that Eve controls everything. I mean, it's not so different from prepare and measure because you could say in the prepare and measure scheme, Eve controls the channel through which information is sent. But in a way, it's even in a sense, conceptually simpler to say, actually, Eve produces something. It's completely under, so by saying Eve, I mean it's not under control of Alice and Bob at all. Sends stuff to Alice and Bob, and then Alice and Bob can, by just communicating classically, make sure that they get something out of that, the key, K, which is then secure. Of course, as you know, it may happen that they will abort the protocol and not generate the key, but they can generate the key, which is, if it's generated, guaranteed to be unknown to the adversary. And this is, if you write it down in that way, it's almost obvious that this can never be achieved classically. And I mean, this is maybe a variant of Shannon's theorem, and what you heard from Uli, that I mean, you could even do a proof in a similar fashion, that if you want K to be something that is unknown to the adversary, you will not achieve that as long as, of course, the adversary also can overhear this whole classical communication, because, and the reason is simple, because Eve just knows everything that is needed to generate K. So you can, in a sense, think of K being a function of everything else, if you think classically. And then, of course, if K is a function of everything else, and everything was produced or at least overheard by the adversary, then it cannot be unknown to the adversary. So the adversary can evaluate that function. And now it's a very interesting fact, and I would say this is even at the core of quantum theory, that information doesn't necessarily, so even if it exists somewhere, it's not clear that it can be copied. That's no cloning theorem, but in this scenario it just shows that there is a certain flow of information which starts from Eve and ends here at the key, which has the property that even if Eve here has a memory E, which could be an arbitrarily powerful quantum computer, we will end up in a situation where the density operator describing the key and the adversary is up to some approximation, and I will later talk about the approximation. That's why I talk here about inequality. Is here, okay, that's a notation I will use repeatedly. I write here the identity that divided by the dimension of the system K. So K is a key system. For example, you could think L classical bits, and the identity just means it's a uniform distribution. It's just a short way to describe uniform distribution. And the reason why we call it identity is because if you represent the uniform distribution as a density operator, it's proportional to the identity, and that's you have to divide by that to make it a normalized density operator. And then and that's the important thing, it's independent of some other state, which in this case I could even say it's the same, it's the marginal on E. So we get an independent statement, or we get a secrecy statement, if you like, or you could even say it more generally, we can say something. So this is a statement Alice and Bob can make. Alice and Bob can make a statement about Eve, although they have no control about Eve at all, but they can make the statement. So this is maybe the important thing. Alice and Bob, from their knowledge, can derive that statement based on what they see here. And this is, I think, remarkable. That's one of the things that fascinated me, at least from the very start, that there are these, like, at the beginning, if you think classically, clearly very counterintuitive facts, because I just gave you the classical proof why this shouldn't happen. And of course, our intuition is driven by classical considerations. So this shows you there's something interesting going on. You can make a statement about something you have no control over. You cannot observe it. Eve has maybe never been seen, and we can make that statement. And this is particularly interesting for physicists because we have in physics also very different systems where the same happens. For example, black holes. So you can imagine that there is an observer here, A, okay, suggested could be Alice. There's another observer, B, but the idea is now these are just physicists, they're not cryptographers. And there's a black hole here. Now, unfortunately, I cannot draw a black hole, but I have one as a screensaver, so you should imagine that. And now, you may have heard, it's the famous result of Hawking, that black holes radiate. And you will already see the similarity of the picture here. The picture I've drawn here. That was another reason why I chose the entanglement-based version. Now, of course, the observers can talk to each other. And at the end, as physicists, this has now nothing to do with cryptography, we want to make statements about what is at the inside of the black hole. So here I call it now the inside E, just for reasons that are now obvious to see the analogy. And so what quantum gravity people who are following this, what is called it from qubit approach. So they're using information theoretic methods to make statements about, for example, black hole physics, which is a special example of a quantum gravity situation. They now can make statements about the state, and here maybe I call this not key but R, so that's the Hawking radiation. The Hawking radiation and how it's correlated to the inside of the black hole, or whether it's not correlated. And some of the big questions are really, is this Hawking radiation correlated to the inside, what happens at the inside, and so on. Now, this is not just an analogy. It turns out that the techniques I will tell you about, and these are very specific techniques, the smooth entropy calculus, the Definetti theorem. There are also other things I will not use here, but that are used in information theory, like information recovery, which is some technique that tells you how do you recover information when you lost parts of it. It's related to error correction. And also other things like maybe I've heard of the decoupling technique, which is actually a quantum version of privacy amplification. all these techniques that are used in information theory are actually by the researchers here applied. So when you go to a quantum gravity conference, to an ETH from qubit conference, you hear about smooth entropies, you hear about decoupling, you hear about all these concepts, and they make very similar calculations. And I hope I could illustrate that this is not a coincidence. In both cases, we are dealing with a system about which we know basically nothing. ETH in this case, and in that case, the black hole. So if you are interested in black hole physics, you can, in whatever I'm going to say in the following, replace ETH by a black hole, then you will get interested in state of black holes. So then I would turn back to QKD. Okay, so that was the motivation why it's even like there's a larger interest, even if you're not interested for some reason in applications, you could say actually studying quantum cryptography gives you a lot of insight about how information is located in space-time and so on. And conversely, we need to understand that to make progress in quantum cryptography. We need to understand how to formalize these things, and we will see certain parts of that. Now, okay. Maybe one last general remark before I start with the technical content is, William Maurer already mentioned that I graduated with him as a PhD student, and I think one important thing you learn in cryptography, and in particular when you're a student of William Maurer, is, I could phrase it in a negative way, you get paranoid. But to say it in a positive way, you really are trained to make all the things you're doing explicit. So you shouldn't forget something. In a proof, you have to write down everything you're using. And if you're not writing it down, you're probably not aware of it. And if you're not aware of it, of an assumption you're making, it could be that the assumption is simply not fulfilled. And then when you build a crypto system, and then of course an adversary can exploit that fact. And this happens. And I think we heard already of examples of that. So cryptography is a very good school to learn to make everything explicit. And you cannot just do hand-wavy arguments. So a physicist would typically say, if I do an experiment at CERN, I have n particle collisions. Now I need to analyze them. Let's assume the second particle collision was independent of the first and the third is independent of the second. So we assume what is called the IID. And maybe there are good reasons to say in practice that assumption works. But in cryptography, in particular in quantum cryptography, where the state is completely controlled by the adversary, there's simply no reason to make this assumption, at least not as an a priori assumption. Maybe you can make other assumptions and then derive it. So that's another thing, that cryptography is in that sense a very nice way to learn and to train oneself to not forget to make assumptions. And I think this training is sometimes missing when you talk to physicists who didn't go through the cryptography school. And to say some last remark about that. So for example, physicists would assume that if you generate black holes at different places, seemingly independently from independent matter shells, then the black holes are the insides of the black holes are uncorrelated. And now recent calculations actually suggest that this is not the case. So even if you build black holes in remote places, they are somehow, in the internal degrees of freedom may be correlated. And this is just because we made certain assumptions about space-time, about separation in space, which are very intuitive, but apparently not true in quantum gravity, where things are sometimes not as intuitive as we hope or think. Okay, now I definitely move to the pure cryptography part. Okay. Or are there any questions about this so far? So I will now immediately move to a very concrete question. So I wrote.
Can I ask a question about this?
Yes, sure. So,
maybe just a short question. What is the most important open problem in black hole physics? That is what can I imagine are they interested in?
Okay. Okay, this question makes me a bit nervous because Ramona told me several times to talk about black holes, but I'm allowed to answer the question. So I think the big question there, and this is probably different in a sense from cryptography, is that we don't even have the framework in which we describe everything. I think the really big question is that we have, in this scenario, we have quantum physics, which of course we know, and we have gravity, and the two don't fit together. And now you can think of black holes are concrete objects where we already know, due to Hawking's calculations and arguments, that both quantum physics and general relativity have to play together. So, for example, Hawking radiation is an effect that can only be explained if you take both theories together. You already see that actually in the temperature formula for Hawking radiation, which involves the gravitational constant and Planck's constant, which is just a sign both theories are relevant. And so we don't know how to fit them together, and a black hole is kind of a nice object. It's, in a sense, maybe people think it's a complicated object. It's actually an extremely simple and clean object to study how these two theories may play together. And in order to study that, one considers now correlations and asks what's the entropy of this radiation, very simple questions. And one can think of, this is again a very general comment, when we analyze cryptosystems, we mostly work with entropies. You have seen that in Norbert's talk in particular. And entropies are also used in thermodynamics. And if you think back about why was thermodynamics successful even before people were aware of the molecular structure of gases and stuff, so we didn't know about atoms, but we could still build steam engines which are based on the theory of thermodynamics. It's just because the concept of entropy is so general. And so what we can do also in black hole physics is, although we don't have the full framework, it's already possible to calculate entropies. So that's why it's not that we can now ask more concrete questions, how does it really look like if we watch inside, but we can talk about entropies because the notion of entropy is so general. So one could say the more concrete questions is about information flow in space-time. Okay, now you saw I wrote down a quantum state. And actually, the first question you need to ask, and this sounds like a philosophical question, but QKD makes this an extremely concrete, practically relevant question, is how do we interpret the quantum state? I mean, probably I've heard about different interpretations, or have people heard, so who knows an interpretation of quantum states? Yes, Marty? Which one, for example?
Maybe as state of knowledge?
Yes, so it could be a state of knowledge. There are also other interpretations, like related to frequency interpretations. And now we actually need to, for the purpose of QKD, at the end we want to make an operational statement. And so we need to ask which of the views on what is the quantum state is at the end the operationally relevant one. Now, one thing that is important is the following. So I wrote down here this state, which is now in the QKD case a key of length L. So maybe I could say, let's suppose so I will use the same notation to describe K, the key, as a classical random variable. So I wrote the key with values in which is a bit string of length L. So I can do that. And you're probably already now from Norbert's talk familiar with what is called, or how we represent classical information in a quantum state, but let me still write it down once just to fix the notation. So if I want to express the fact that there is a classical key which is potentially correlated, before I know this equation, with some quantum system E, what I can do is I can write this as a sum where now I will write small letters for concrete values that the key can take and use capital letters to describe the system or the random variable in which the key is stored. And then we have a probability, P, K, so and this has now two Ks, so this means it's a probability distribution of the key, and this is what's the probability that the concrete key K occurs. And then this is now what you have seen already in Norbert's talk, or I think partially like that. We can represent the actual value of the key in a register that has also the label K, so there are many Ks occurring. So this is a het and a bra. This is just a state that encodes that the key is now this particular bit string. And now in this sum, so this is all in this sum, there could also be a quantum, there is some state or some density operator E that may, of course, now generally depend on K. And if it doesn't depend on K, then we get, and if the distribution is uniform, we get its form. So that's this state. Now, what is important is that this K now is a K that comes from the whole bit string that is generated. So if I look at the marginal state on the row K, that's basically now just a different representation of talking about the probability distribution of the key. So the question of how to interpret the quantum state is linked to the question of how to interpret the probability distribution. And now we can ask that question. So what are possible interpretations? If I now only look at this simpler object, I forget for the moment the E system, I just ask what does it mean to say the key has a certain distribution. Now there are two big schools, and I will not go much into them, but I will just write them. So there's a frequentist interpretation and a Bayesian interpretation. Now, what is important is that the frequentist interpretation is something we cannot apply in this context, simply because if we want to be operational. Because the frequentist interpretation assumes that the experiment that is defined by this probability distribution is repeated infinitely often. And then you look at the frequency of how often things occur. Of course, we can always hypothetically think of that, but in the actual thing, in the actual scheme about which we want to make a statement, the generation of a key is not going to be repeated. And even if you say, okay, I can use the device twice, but of course there's no guarantee that the adversary, if you use it the second time, will again behave in the same way. So if you really want to match the concepts with something that is in the real world, the frequentist approach doesn't do the job. It just talks about a completely hypothetical scenario where an adversary now behaves the same each time you employ your crypto system, and you also employ it infinitely often, and you are for some reason interested in the frequency of how often different values of the keys enter. Now, the important difference between the frequentist and the Bayesian is, in the Bayesian approach, the probability distribution is not regarded as a property of the system you are talking about. So frequentists would say, okay, if I, for example, have a coin and I flip it many times, it's equally often heads and tails. So the probability distribution of 1/2, for example, is a property of a coin. It's a fair coin if it has probability distribution 1/2 of showing both outcomes. Actually, this example already shows it's problematic, because if you repeat the coin toss many times independently and you analyze it with classical theory, it will always land exactly on the same side. So actually, it wouldn't even work in that simple example. In the Bayesian view, you say a probability distribution is not a property of the system, it's a property of the knowledge someone, for example me, has about a system. For example, if I say the weather tomorrow will with 50% be sunny here, then this has nothing to do really with the weather. Maybe it's somewhat, it has to do with the weather in the sense that maybe I looked at the weather forecast, but it's just my knowledge. If you ask me what's the weather in Australia now, I would probably say it's with 80% sunny, because it's often sunny in Australia, but it has nothing to do with the actual weather. It's not a property of the weather there, it's just a property of my knowledge. It's 80%. It's nothing you find in the atmosphere. Now, if you generate the key only once, which we do here, then you just cannot employ this approach here. So the frequentist doesn't work, as I argued. So we are basically left with this interpretation. And this will be important for the following reason. Whenever we now in the following write down a density operator, we have to ask ourselves, whose knowledge is that? And so now, before, or probably also in the lectures of Norbert, this density operator appeared. But the question is now, whose knowledge does it characterize? Is it Eve's knowledge? Is it Alice's knowledge? So who thinks it's characterizing Alice's knowledge? Okay, who thinks it characterizes Eve's knowledge? Okay, so it's, in a sense, neither of the two are true, because I was not precise enough, in a sense. So, first of all, it's certainly not Alice's knowledge once the protocol is executed, because Alice will know the concrete value of the key. So for Alice, it would be absurd to say, the key is now uniformly, I generated the key, I saw the bit string is 0, 1, 1, 1, 0, but it's actually uniformly distributed. That doesn't make sense, because her knowledge says the key has that particular value. So it's in the probability distribution, it's a peak distribution where just that value has probability 1. Now, I think a majority said it's Eve's knowledge, but this, for that state, is also problematic because Eve is herself part of the thing you describe. So, you see, the E system is Eve. So this would be as if I make a statement about my own knowledge. And maybe that's somehow possible, but it certainly leads to problematic recursions in a certain way. So this is also not how we characterize. It's not, this density operator is not the view that the adversary Eve has on the system. So what it is, but of course, I mean, it makes a lot of sense intuitively. That's what we want. We want to say the key is somehow independent of what the adversary knows. So it's like an outside perspective in a certain sense, but you could also say like that. It's the knowledge that Alice has before she starts to run the protocol. So before she starts the protocol, she could say, okay, the key is now, of course, uniform from her perspective, and it should be later uncorrelated to Eve. But it's important that you make the distinction. So I could say this thing here is, I write here, for example, I could write this is Alice's knowledge at, let's call this time t0. That's before you start the protocol, but the key is, of course, generated at the later time. So now what you have to realize is that when we talk about the quantum state, the time at which we have the knowledge from which we characterize with the state is not the same as the time of the objects about which we talk. So for example, I can talk about the knowledge I have of a coin toss I make and the outcome of the coin toss in a minute. But I can now talk about the knowledge I have now about it. And of course that knowledge will change once I've made the coin toss, and you'll see it will be different. So we have a different time here. So the time here is when I make the statement from a certain perspective, and here these things could be things that are only generated later in time. So that's very important in quantum theory to think in that way, because otherwise you run into, at some point, into difficulties. Of course, this is always implicit in a sense, and the question is also, how do we know, if we analyze a protocol, what is Alice's knowledge at the beginning of the protocol? Now the important point will be, we will never write this state or the initial state. So, okay, maybe I'll sketch it like that. So let's suppose Alice has at some time t0. I will now not always write Alice. This could be any person at time t0. Had some knowledge, and the knowledge is about, let's say, the state of the world, maybe stuff that is in her lab. Let's call this L, and I put here a 0, a little 0. It's just indicating the stuff at time 0, and maybe also Eve's knowledge at time 0. And now we will execute a protocol. So Alice will execute the protocol, but she still talks about the knowledge she has now at time t0 about what will the protocol produce. So there will be a new state, which is, however, also still her knowledge at time 0, but however, it will be about the key. Let's say here is times, I mean, this is the time 0, and the key is now produced at time 1. So I will call it K1, and also what's the Eve's information at time 1. So what we are interested in at the end for the security statement is to say this state here is now close to that thing that I wrote down, the identity tensor rho E1. And the statement we are going to make is that independently of what that state is, so for all possible states, we will end up with that state. So, and that tells you that at the end, we don't need to characterize Alice's knowledge at the start. So we can sell a crypto system to any Alice independently of what her knowledge is. So basically you could say, if you do a security proof, you make, what a security proof is going to do is to say whatever initial knowledge you have about what's now in your lab, if you execute the protocol, your knowledge about what comes out of the protocol is that the key is secure. So this just means you can sell the crypto system to a person independently of what the knowledge is of that person. So that's one way to think about it. But I think the main point to keep in mind is that whenever we will in the future write down a density operator, we have to keep in mind at what time the knowledge is taken. And this can be different from the time at which the objects exist about which we are talking. Yes?
Isn't the key produced at late times and not equal to 0?
Yes, right. That's a good point. So the key, so that's important. The key is produced at time 1 and not at time t0. Nonetheless, let's suppose I now start the protocol and let's say it takes an hour to run. I can now say what's my current knowledge about the key that will be produced in an hour. So it's not a contradiction that here is an earlier time than it. That's the whole point. Actually, whenever we make predictions in physics, we do that. So whenever we say what's the quantum state of a system, we are actually, or when we make a prediction of at CERN, let's say, to return to that example, I make a prediction about the outcomes of measurement at CERN. But to make a prediction, of course, it's based on the knowledge I have now as I make the prediction. So implicitly, when physicists write down a density operator, this t is always the time at which they write the paper, and then the experiment is carried out later. And the thing here, talk about the stuff that will come out when you run the experiment. So there are really 2 times involved. And we are often not aware of that. So that's, again, one example of cryptography. It just forces you at the end, if you make everything precise, to reflect about these things. Okay. So that was just a short example of how thinking about cryptography influences thinking about basically foundations of quantum theory in the sense of what does it even mean to write down a density operator. But now we will use this later, but even if you didn't fully get that, that's at the moment not so important. I will now start with, let's say, the part where we talk, I mean, the title is Foundations, where we will do 2 different things. The foundations of cryptography will contain, on the one hand, a clear specification of what does it mean for a key to be secure. So what do we mean when we say there's a secure key or an approximately secure key? What does the approximation mean? That's what Norbert already indicated, and I will talk about that. And the other part on the foundations will be what are actually the assumptions going into quantum cryptography. So when we claim that a key is, a protocol is secure, what did we assume that quantum theory is correct and so on or not? And there was actually recently, or not so recently any longer, some time ago a paper by Dan Bernstein. You probably know him well. He can, he's a special person. And he, for example, said these security proofs in quantum cryptography cannot be correct because he read them and at no point is, for example, electrodynamics or quantum electrodynamics appearing in these proofs. But the world is described, obviously that's a law of nature, and if it never appears, how can you claim that the security follows from physical laws if you never use the law? So we have to be precise. What do we actually use? Why is it actually irrelevant in quantum cryptography how the laws of quantum electrodynamics look like? So these are things that if you ask, or yourself at the moment, maybe you already have some knowledge of quantum cryptography. If, let's say, someone comes now and asks you, you're a quantum cryptographer, what are really, when we say that security follows from physical laws, that's the slogan that we have in quantum cryptography, what precisely are these laws? What would be your answer? Is it quantum electrodynamics? Hopefully not quantum gravity. So what would be your, does anyone have an answer to that question? I mean, that could happen, someone asks, because we always make this statement, security follows from physical laws rather than computational assumptions.
The no cloning theory?
Yes, that's, I think, a good answer, although one could say this is not a fundamental law. This is something we derive. We have it's a theorem, the no cloning theorem. So what are...
Inherent randomness?
So?
Inherent randomness?
Yes, we will talk about that, but that's usually also not if you open a textbook, quantum theory book, it will not talk about that randomness in a way that is in here. It will just say, okay, the outcomes are kind of looking random, but does this really mean they are truly random? But that's a good, already good answer.
The uncertainty principle?
Yes, but that's, again, I think, okay, I mean, these are all correct answers, but I would say they're all derived notions. If you read the standard textbook, they start with some axioms of quantum theory. And then these are derived things. Then there's the chapter on Heisenberg uncertainty, and then it says we can now derive the uncertainty relation. Yes?
Quantum mechanics is correct and complete.
Yeah, that's the correct answer. What does correct mean?
No contradiction.
Yes, but if you say quantum mechanics is correct, correct has to be relative to a theory. Like, I mean, correct means it satisfies this and this and this law. So you cannot get around still specifying. I mean, it's a good answer, and I will express it almost in that way. But what is the correctness referring to?
The axioms of quantum mechanics?
Right, yes. Yes. So we have certain axioms of quantum theory. Maybe those who, I mean, this is already actually driven by now quantum information. If you open a standard textbook on quantum theory, an old one, there will be no list of axioms. It will just at some point say there's a Hilbert space and there's the Schrödinger equation. And this is not a good basis to do quantum cryptography. Then, for example, if you open a modern book on quantum information theory, or even a not so modern one like Niels and Schwang, you will find these axioms, and this is then what is based. And these axioms are more general, that's the important point, than, for example, quantum electrodynamics. The axioms are about the structure of information, in a sense. So you already need to go to a modern formulation of quantum theory to actually see what are the laws we are talking about. And this will be another thing I will treat in detail. So let's talk first about what does security mean. And before I really go into the definition, I want to introduce a kind of graphical notation, because I don't want to write down too many formulas. And you should understand the notation in a sense, in the sense of abstraction that Uli Maurer introduced, namely that one can make everything in principle axiomatic and just talk about these pictures and actually define operations, what it means to draw the picture and combine them and so on. But you could also then say, okay, these pictures could be made more concrete in a concrete physical system. So let me give an example. So let's say we want to, I mean, you already are very familiar with the one-time pad. And in this graphical language, I could describe the one-time pad in a way which is very similar to what Willy showed. I think there was almost an identical picture there, where we say we have a box which is the functionality that generates the key. And now, okay, I have to now get used to, I decided I will use the computer science convention here. The problem is in the physics convention, time always runs upwards in space-time diagram. Now in computer science it goes down for some reason, which is probably the better reason, because we read from up. Usually I read text from up to down.
The paper roll goes down, you
yes,
start.
Right. I don't know why the physicists have this.
We work on the toilet, you know, and then we write downwards.
Yes, they just have a t-axis, because it's a diagram, it has to go up. So I may make some mistakes. So let me try to stick with going down in time. And so I can write here something like, okay, I'll write here. That's a risk. You can think of this a functionality. I call it a functionality. You could really think of, if you want, pictorial as really a box somewhere, but it's of course not a physical box, because it's something that extends over space. So let's suppose here on the left you have Alice, and here we have Bob. So in reality, this is of course not a box that spans from Alice to Bob, but we could imagine it's we put the box around these things, and out comes a key. So here comes out the key. Maybe there's also potential stuff going to the adversary. So the adversary is always shown in the middle somewhere. And I will use this symbol to say that the information that leaks to the adversary, or whatever gets out of this box, will be independent of everything else. So you could produce it without looking into that box. So this just basically means that if I draw this box, it really means you have a distribution that satisfies this property that I didn't now write it's uniform, but that's what I mean. This box produces systems which are in that state. That's what I mean formal. But of course, if one actually really implements them, one has to be more specific and say at what time exactly is this key output and so on, and I will abstract away from that. I will just say we have some box that generates key and time order goes down, so we can now use the key if I draw here something else. And so here we have, for example, an authentic channel, let's say. So authentic is necessarily classical, because you know that we cannot have an insecure but authentic quantum channel, because in a quantum channel, whenever we read something, we also change it. So that's my implicit understanding that when I write authentic, it's a channel. So let's suppose this is, for example, a channel going from Alice to Bob, or it could even go both ways. Maybe I don't want to restrict myself. And then what I have here is also, so this authentic channel will leak stuff here. So, okay, let me still say, if I call this communication C, that is input here, then it also goes to the adversary. So this is really like that. And now I think this is also similar to what you have seen in the talk of Uli, is I could now write a box in this vertical direction, which denotes a kind of protocol. So this is what Alice does locally. So for example, she would take the key and maybe you get a message from the outside. So on the left, okay, probably cannot see it from here, but there's just a message M going in, and then the adversary computes something, namely he computes, for example, if this is bitwise, the XOR between K and the message, and then Bob also does a computation and produces some M prime, which is the key and the communication, the ciphertext you got, and outputs here M prime. And now you can show that, I mean, a priori we could say maybe these keys are different, but if they are equal, we can show that the message is equal. And now is what we then can also show, I will not do that because that was already done, we can show that this C will be independent of the message. So it's secure. But I just want to introduce the graphical notation. So part of the notation is the following. If I draw now I could now draw a larger frame around this, and now I can say this is now again a system that just takes as input some message M and outputs a message M prime on Bob's side, and here the arrow now goes here to the outside. It produces some C, and if I now want to ask myself what is the functionality of this larger system that I've constructed in that way by plugging these protocols in, so these boxes I call protocols, I could now ask what does it do? I could now draw another system and say actually what it does, or what I want it to do, before I do the proof I may not know, is that I want to have a system where I get a message in, I get a message out M prime, or the same message M out, and here whatever comes out here is independent of that message. So now we will see lots of such drawings, and what we usually want, and I think I will now use this notation that was briefly mentioned by you as well, which means as secure as. The way to think of this, which is best suited if you want to think concretely, because this now looks abstract, and you may be familiar with the formalism of quantum theory, for example, completely positive maps. And you are probably trained to say that whenever you have a channel, for example, a communication channel, you can describe it as a completely positive map that takes M as an input and produces C and this M here as an output. You can think of these graphical box, or these boxes that I'm drawing, as specifications of these maps. So what I mean by that, there's maybe not unique, but there is a set of, if you write down a completely positive map and tell me, please look at it, is it one that I mean here, then I could decide yes or no. So it's basically, this stands for a whole class of maps whose details you may choose. For example, you may choose to say that nothing comes out here, and that's still compatible with this picture. So I would say this picture this fulfills the specification of that picture. If you somehow say this always outputs a 7 here for some reason, or a 42, then I would say it also satisfies it. So this is a class of maps here as well. because there's some freedom what comes out here and so on. And this relation now means that whatever, if you use this degree of freedom you still have, but satisfy the picture here, then what comes out will also satisfy this specification here. So that's how you should think of it. So you can really think of completely positive maps. I just realized when I talk sometimes too abstractly, people ask us, but what do you mean? So you could actually formalize this by writing down concrete maps, which you also need to do calculations in using the quantum formalism at the end. Okay, so that's the type of notation I'm going to use. And now I will probably... Maybe we could immediately start now asking ourselves, what's now, or, okay, I don't know, I don't remember how much, whether you use the term real world, ideal world, formalism or something like that. I will sometimes, okay, it's probably not a good, necessarily a very good terminology, but the way you should think, I have here two pictures, and I will always have two pictures next to each other related by such a symbol. And the idea is typically, here on the left, we have given resources. For example, a secure key and an authentic channel. And on the right is some new resource. For example, here, a secure channel, which we want to achieve. So we have kind of the given resources and the target resource, if you want. And sometimes people use this terminology that they say, this is called the real world. That's what you actually build. And that's called the ideal world because that's what you want to have. Now this terminology is really not good because we will do it stepwise. So we may use again the secure channel in another construction where it's part of the real world. But I may sometimes accidentally use this terminology to just distinguish the left and right hand side. So now, when we...
Can I make a comment?
Yes.
I think we should understand both statements about the real world, except the right one is more abstract. It says less, but maybe it's more useful, because if you look at it, you understand what it's
Yes,
saying.
I agree. Maybe I really shouldn't use this term. But maybe you should understand it as a remark if you have heard about it, because if you look at literature, you will see this terminology, real world, ideal world. But I agree, it's not, I mean, at the end we want to talk about the real world, and this is just a more abstract description. You could say in the real world we actually have a protocol, but we're only interested in knowing the functionality on this abstract level, and that's why it's also part of the real world. Now, what do we want to do in a security proof? In the security proof of QKD, so let me just, this is kind of the outlook of what we are going to do in the total of the 3 lectures I will give today and tomorrow. Is we will have certain resources. So what are the resources that are given in QKD typically? Does anyone know that? So which boxes would I draw, which are typically the things we are starting off with? We have to start from something.
It sounded to me like one box is an arbitrary quantum state, non-specified. It's just a quantum state, right?
Yes.
It's ETH.
Right,
That's
yes.
it.
Right. That's precisely the case. So we could say one thing is just some box which only outputs stuff on Alice. I mean, okay, I will no longer describe. Left is always Alice, right is always Bob. It outputs systems which I call A and B and E, but we know otherwise nothing about this thing. It sounds like a completely useless resource in a sense. Now we need something else, of course. Somewhere we need to break the symmetry, because here Eve is equally powerful than Alice and Bob. So what breaks the symmetry here and makes Alice and Bob more powerful? Yes?
Classical channel.
Right, it's a classical authentic channel. And we have heard a lot about authentic channels. In particular, I think you made the point very clearly that it doesn't matter where the authentic channel comes from. We don't necessarily need a key. And actually, there are weaker resources. There are, again, protocols that start, for example, from weakly correlated strings, some passwords that are not uniformly distributed that Alice and Bob share, from which they can still get authentication. So this is let's say, an authentic channel. And now you already see the modularity of this. So later, when you have another protocol that generates an authentic channel from some different weak resource. You can just say you have achieved that, so you plug this in, and whatever we prove here also works for that. So you make that step repeatedly. We will see that, how this concatenation works. So the authentic channel is something that just takes communication here, but also potentially outputs it to the adversary, but there's nothing here coming in. So I will denote it maybe with this arrow just to emphasize it's authentic. And now, how detailed should I draw? Yeah, maybe on the right hand. So if we are in QKD, we are interested in having a key. Of course, at the end, we want to send a message, which we do with a one-time path. But you now see that in this step, in the QKD step, we are interested in building that thing. So maybe I should use some color code and say, okay, now we have already heard from Uli that if we have a secret key or a secure key, okay, maybe, I mean, I use this synonymously, secure and secret, maybe. Yeah, we will see what the conditions are on them and why both terms may make sense. So now QKD is actually the task of creating this blue, constructing this blue functionality. That's what we want to do. And once we have that, of course, in the actual world, if you look at on the detailed level, this whole picture will be part of that blue one. But we do the proof modularly. So the modularity here will be important in all what I'm going to say. We will do everything modularly. We will always make small steps. So the step we are going to make when we make this will actually go via different steps. So we'll at the end have here things in between. And then say, through all these steps, we will at the end achieve that, but that thing together will of course be one big relation like this. So we will show that there is a protocol, which is now something like this. So this is the QKD protocol, which will output a key K. Here as well. Maybe I draw this here more down, because it's later. First is this information distributed, and then there's some communication. At the end, some key is generated. And what I want is that this thing has the functionality of a secure key. So that's what we want. So a security proof is, so here you know what's going on. So what is in this box is, for example, okay, in this case it's the entanglement-based protocol, the Eckert protocol. If I would replace this here by an arbitrary quantum communication channel, what I would put here is the BB84 protocol. So choose a basis, send that through the channel, and so on. So all these instructions are part of this box, which I now just draw here as a black box, but you should think of the protocol being inserted here. So these are things, it's like a circuit diagram in a sense where you have elements you plug in, and here you have big elements like a whole protocol that you plug into this diagram. And the security proof will tell you, once you have fixed this, this relation holds. This functionality, if I now draw another box around that one, maybe get another color, like this one, or okay, maybe I make it just blue, because that's, so if I draw this box, this behavior here will correspond to the behavior that in the sense I described before. So that's what we want. That's what the security proof does. And now what we need to do is to be more specific about what is actually this thing. And I already made it specific. I said, it's here, this is just a box which outputs two the key is identical here and here, so it outputs identical keys, and whatever, maybe it outputs something to the adversary, but whatever goes to the adversary is independent of the key. Now, actually the bad news is, if I wanted to prove this, I would fail. There's just no way we can achieve this. And there are two independent reasons for that. We have to do two relaxations to this in order to get to a statement which is actually provable. So unfortunately, if I leave it like that, I would have to say, this is impossible. I could even give you an impossibility proof, which is quite easy. Maybe you can think yourself about it. But what do you think? What are the problems? What is at least one problem we will have? Are there any ideas? What could be Why is it too strict to require this? Yes?
There is the classical leakage on the left, which is not going to work.
Okay, that's a good point. You're saying here there's also some C coming out. Okay, maybe I should, okay, that's, maybe I could say, okay, let's call this, here I don't care what comes out as long as it's independent, or maybe I call this here E prime, because at the end so there's something E prime, and I call this together, let's say the E prime comes out here, and the C comes out here. I mean, that's a good point, but that was not the point I was trying to, and I call this together E. And then that's fine. So that's the classical leakage is kind of included in whatever I have here. But thanks for making that remark. Are there other things which could be problematic? So Uli already said this state could be arbitrary, but of course an arbitrary state could also just be one that consists of basically empty systems that have no correlation. Like let's say ETH just distributes, for example, classical information to Alice and Bob, then clearly they cannot generate the key. So the problem is that with this thing we have no guarantee that a key can be generated. So if you think of a concrete QKD protocol, we will at some point have a parameter estimation, and if the state is distributed by the adversary, or by whatever device that we think of being potentially under control of the adversary, if the state has not enough correlation in it, or doesn't satisfy the entropic equations that you've seen in Norbert's talk, then then Alice and Bob have to abort the protocol. So what you will achieve is here something that will also output nothing. So we have to become more modest and say, actually what we have here is not that box that for sure outputs a key. It's actually, and that sounds very bad in a sense, but it's like that. The adversary can actually completely choose whether we get a key. So it's actually an input of the adversary. And if I want to be general, and I think this is even easier, I could say there's an input of the adversary, because that also takes into account what we have heard from Uli's talk, that the length is leaking. In this case, I could say that length is actually even an input from the adversary. So the adversary can choose how long the key is that Alice and Bob get. And now the key is now a bit string of length capital L, where L is that input. And that's really the best we can achieve. So we cannot force Eve not to cut the communication and just inhibit any secure communication between Alice and Bob. So the only thing we can hope for is that if Eve allows Alice to communicate, if she doesn't cut, she decides not to cut the optical fiber connecting Alice and Bob, that's a decision that Eve has to make. If she decides not to do that, that's like choosing the L to be non-zero, then Alice and Bob get a key of length L. Okay, maybe this sounds a bit frustrating, but it's just saying in more trivial terms, Eve, under the assumptions we are making, which is that Eve, or the non-assumptions if you want, that Eve is not restricted in whatever she does. She has complete control in the quantum communication between Alice and Bob in both the entanglement-based and prepare and measure scenario. She has the choice to make the key zero length or trivial by just choosing to cut the line. Of course she can do that. We cannot prevent that. Okay. That was the frustrating part of my lecture. Now we'll get to more positives.
So the L cannot be like infinity, right?
Yeah, okay. Now, okay, the question is what is the range of things? This will depend on the protocol. So actually L will be typically a number between 0 and some L maximum, where L maximum is actually dictated by the protocol that Alice and Bob execute. Because Alice and Bob, actually, they usually assume Eve is nice in the sense she's just not there. Because, of course, if Eve... So, I mean, maybe it's misleading to say this is an input, because you may think of the input of something that is actively chosen. But if there is no Eve, what happens is that the input here is just the maximum length that the protocol has in the most optimistic situation where there is very little noise in the channel and so on. So basically not disturbing the channel between Alice and Bob means in this abstract framework choosing an L that is large, but it cannot be larger than the amount of key Alice and Bob plan to generate using the protocol. Thanks for the question. Okay, so that's the first change you have to make, but now still we will not be able to achieve that. There's a second problem, and maybe that's something you could infer from what Norbert said. Does anyone have an idea what could still go wrong here? We still have to weaken it, so we cannot, yes?
The keys might not align all the time at least.
Right. It could happen that sometimes, with although a very low probability, this key that Bob gets is not identical to Alice. Exactly. So more generally, with very small probability, something could go wrong. It could also be, I mean, that's absolutely correct, but it could also be that with very small probability, ETH is actually correlated to the key. For example, and I think this is clear from the protocol description that Norbert gave, if in the parameter, or if ETH always guesses correctly which basis Alice and Bob chose. I mean, of course, the probability is very small for that, but it's not zero. So with some probability, ETH could perfectly guess which basis, and if she just tries with that, she makes a guess and attacks the protocol under the assumption that this is correct, then if she was right, she will read the complete key, and Alice and Bob will not notice. So there is a small probability we will not achieve that. So we have to make this definition approximate. And I will typically do that in this graphical formulation just by saying I write here a little epsilon somewhere, which means that, and I will be more precise what it means, but roughly speaking it means that you achieve this functionality up to some probability epsilon error. Now the question is, what does this mean to have an error? Now it's clear in the case of the key being not identical. So this epsilon, for example, says the probability that what Alice gets and what Bob gets as a key are not identical is upper bounded by epsilon. But how do we phrase the same for the adversary here being correlated? How do we say that the correlation only occurs with probability epsilon? That's a bit more tricky. But it can be done. And let me, okay, I don't know. Yeah, we have enough time to do that. Are there questions so far? I'm actually faster than I thought, so you should feel free to ask questions. Yes?
Maybe just a quick question. So you said Eve could just guess the basis we're measuring in. Mm-hmm. Could she also just guess the key? Is that also included in that epsilon, or is that part of the ideal world? We just accept that she can still just guess the key.
That's an excellent question, because that's something many people get confused about when we talk, for example, the standardization people. Norbert really suffers from these things a lot. So that's really an important point. So let me explain that. So if you have, let's say, we will have a, so what we want in the ideal situation, so we have this state which is independent. Like we want things to be in that situation. So even in this ideal situation, Eve can of course just say, let me guess the key, let's guess the key consists of only zeros. And she will be right with a probability 2 to the minus the length of the key. However, there is no way Eve can know that she's correct. So actually, in this case, this is in a sense an unproblematic case. You could say I could always make a guess, but because I can guess things about the world, but it doesn't change the world. I make just these guesses. It would be problematic if Eve knew that, she can make a guess and someone would tell her, actually this guess is correct. And this happens in the attack. So without an attack, she can always say, for any possible value, the guess is that. That's just what that means. That's basically just saying, what does it mean that the key is uniform? She could only guess it with that thing. So that's unproblematic. But what we want to avoid, by definition, this is unproblematic because we say this is what we want to achieve. Now, in this attack, there's something very different happening, because if Eve chooses the basis correctly, Alice and Bob will accept and say, now we generated the key, and then Eve knows that she knows the key. So she has there's a big difference between just making a guess and leaving it like that, or making a guess and then someone tells you this was the correct guess, and that would be something very problematic in a sense. I mean, it's not very problematic because at the end when we make this episode, we are going to tolerate it, but it's, if it happens, under the event it happens, it would be problematic. Yes?
I mean, if she guesses the key and she can listen to the ciphertext, can she just use it and make sense if the message makes sense later?
Yeah, that's also a good question, and the answer is clearly no. But it's a very good question, because that's typically what you would think. You'd say, okay, now Eve can still make a guess, but now think of the following. Now I could, let me apply a one-time pad. I could now convey, let's say I write down a one-time pad bit here on this thing. So, okay. Has anyone seen what I've Okay, it's only one bit. Now I communicate some very important information. For example, whether I will be here for the lecture in the afternoon. That's kind of important for you. Using a one-time pad encoding. So let's say 0 means I'm not here, and 1 means I'm here. But now I use this as a one-time pad. So of course I communicate it to Ramona. She needs to know whether I'm here or not. So, okay, Ramona needs to know the key. Now it's not readable even here. Okay. That's the key. No one else has seen the key. Okay. Now my answer is 0. The ciphertext is 0. Now does anyone know whether I'm more, I mean, does this information give you any, I mean, you probably guessed I'm going to be here, but does it help? Then I now say, the ciphertext I sent to Ramon is 1. That I can send publicly. It doesn't. Of course, you could now say, actually, let me guess that the key is 0, but this doesn't help you because both answers, you see, you cannot. And generally, you can say that so this is different. I think the point is, if you do any other cryptographic scheme than one-time pad, then the point is that it's not usually, I mean, technically speaking, the entropy of the key is much smaller than the entropy or the size of the message. Then you can do that. But in a one-time pad, if it's uniformly distributed, then any possible message, the probability of that doesn't change. So you don't get anything. You can say, okay, you get as many sensible messages as if you didn't make a guess. So I hope that illustrates.
We discussed these kind of things yesterday,
Okay.
or Monday, was it? No,
Yes.
yesterday.
Okay.
And I think what is important to point out that it's not, for this to make sense, it's not necessary to go through all these kinds of potential arguments against. At the end, the argument will just be the right argument.
Yes.
Right?
So actually, and that right argument will be in this example I gave, that this number I sent, when I said I sent the information 1 to Ramona, this number is statistically completely independent from what I want to communicate. So I could just have taken an independent random number generator and produced a number and it would be equally useless to you. I think that's, or I don't know whether you meant that, but that's probably how.
You know, NSA and about the simulation of this randomness.
Yes.
This is exactly what
Yes.
you're talking about.
Yes. Okay, so these are important considerations. Now the point I want to make is, even if it's now happened that with a very small probability the adversary can guess the key and know the guess is correct, this would indeed now violate this. This we have to tolerate. We have to because we know this attack exists and there's no way we can avoid it. I think that it's probably one can even prove a no-go theorem and say you can never devise a scheme because the adversary can always guess what Alice and Bob, make a guess for what Alice and Bob are doing. The guess may have extremely small probability, but it's never 0, and then do exactly what Bob is supposed to do in the protocol, for example, just impersonate Bob without Bob noticing. So in a sense, I think, okay, I don't have a no-go result, but it's probably impossible to achieve that. So you need this epsilon. However, what you will see, we will not do the precise calculations, but we will see that this epsilon can be controlled, and it's actually, okay, are there any experimentalists in the room? Okay, it's extremely easy to make it small. The experimentalists disagree with this completely. It's exponential. So basically the idea is that by putting a little bit of more resources, so let's say I need to communicate a little bit longer, I communicate m bits more, then the epsilon will decrease exponentially with m. The problem is that there's a prefactor that is pretty large, and so this exponential decrease only sets in once you have already made things quite big, so that's why it's not that easy. But at least when you have already a large number of, like a system in which you communicate a lot, let's say a lot means you have more than 10 to the, let's say, 9 signals to be on the careful side, then you can easily make like the epsilon small enough for practical purposes. Now we will have to discuss what it means. So this is actually another interesting thing we will discuss before the break. How should we, or before the lunch, how should we choose the epsilon? Now we have a new parameter. And if I would say, okay, the epsilon is now 0.5, you would be very unhappy because this will, as we will see, mean that with probability 1/2, the thing will, for example, the key will leak or the adversary will know the key. That's what we don't want. Now if I tell you, okay, the epsilon is 10 to the minus 4, would you be happy? Would you buy, like a manufacturer comes and sells you a QKD scheme and says, we did a security proof, it's actually done in a reliable way, in other words, Norbert did it, and now the epsilon is 10 to the minus 4. What would you buy it? So that's a question, that's a concrete question people have to answer, and I think Norbert is now in discussion, or we together, but led by Norbert in discussion with standardization units or offices, and they need to specify this number, they need concrete values. And now, of course, one could go to the safe side and say, let's take the epsilon to be 10 to the minus a million. That sounds very small, but is it really small enough? So these are questions we need to be able to answer. Now you can ask, how do we, by the way, answer these questions in classical computational cryptography? Because these questions must come up there as well. And I think the answer is, there is no answer, because it's just usually an asymptotic statement about, I mean, let's say you would, for example, quantify it with, given the amount, I mean, of course this is not computable at the end, but you could say, if an adversary has this amount of computing power, let's say he has all the computers in the world and can calculate for 1 year, what's the probability that it would be able to calculate or the key or information, relevant information about the key? So that would be a possible definition, at least. And now you could ask, how small could we now choose that epsilon? But the problem is we cannot even make that, we can never make this calculation. We cannot calculate such an epsilon because it depends, first of all, on the machine model, like how much computing power does the adversary have, but it also depends on the algorithm that the adversary would be using. So we would have to optimize over all possible algorithms, and we don't know the best algorithm. So computational cryptography cannot give you this absolute number. It can only give you a relative number relative to the assumption that in order to solve that and that problem, it was that hard, or you had that and that probability, I think you would say. So in a sense, in quantum cryptography, we have the advantage, and I think this is at the end even the core of, we can't really make a firm statement. I mean, if you ask, why should we go through all the pain of doing quantum communication and these expensive devices? At the end, we can make a very firm security statement, which is also quantitative. Otherwise, it would still be useless. It would say there's some small epsilon, but we don't know which one, and that it's secure. If you do it long enough asymptotically, it would be equally useless as I'm saying nothing, basically, because for a concrete scheme, it would tell you nothing. So we need to interpret that. So I will now do 2 things in this quarter of an hour, I think I still have. Namely, tell you how is this epsilon now precisely defined and how should we choose it. And so let me first talk about the definition. Am I now around in the afternoon? Otherwise I will have to...
No, you mixed up the ciphertext.
No, I wanted to scare you. Okay. It's So, first of all, let's say, purely technical definition of the epsilon, which doesn't tell you why we should choose it like that, is in terms of what is called the trace distance, or more generally, if you think of interactive boxes, the diamond norm. Who has heard about the diamond norm, by the way? Okay, so most people. So it's part of the quantum information education, but for those who haven't heard it but have a classical background, it's basically you take the statistical distance of the outputs and maximize over all inputs. And you do that in the quantum realm, but you have to be careful because you also need to make sure you keep somehow a copy of the input, which you do by keeping something entangled and so on. But so I will not go into that quantum definition, because here it's actually, in a sense, a bit simpler because we have no input, we have just a state. So, okay, let me make it a bit simpler, and for the moment, again, ignore the L. So we can understand the epsilon, first of all, for the simpler version of the secure key, which just has a fixed L. So let's say this L is now a fixed value, which I call small l. This is just to make our lives easier, and you have to believe me that we can generalize this definition again when L is chosen by the adversary. These are kind of independent considerations, that making this approximative with an epsilon and making it choosable what the length is. And now I only want to talk about the approximation. So now in that case, it's sufficient to talk about the statistical distance. So you can say, at the end, this whole box that I've drawn is characterized by a quantum state, which I've now written down many times. But now I will write down two Ks, one for Alice and one for Bob, and E. So the K prime should be Bob's output. And now we compare this to something which is our ideal thing. And now I want to be also a bit more precise than before, because I have now Alice and Bob. So we have a formula which looks very similar to the one before, but I now say, okay, there is each key should have a probability of 2 to the minus L, so that's the uniformity. And now Alice should know the key. So here is the index K, that's the system that Alice gets, and Bob should get the same key. So that's the K prime system. So here is no prime, the same key. And then there should be some rho E, which is now not depending on K. And now I have here a minus, so I'm comparing. So this is the state we have from the protocol, from the actual protocol. So let's say I have no color. Let me make it red. So the red thing is now, I need to now distinguish the two things. So the red thing is what we really have. So that's this thing. And now, this is really now ideal in the sense that we never have that in the real world. That's an ideal thing. But I make the ideal now blue. So that's what we would wanted to have if we were not forced to make an approximation, if the epsilon was 0 in a sense. And now we want that these are close, and the technical definition is that these are quantum states. We can subtract them with each other and take a norm. And then we want that this norm is smaller than 1/2 this norm. And this will be relevant for the interpretation, smaller than epsilon. So that's a technical definition. That's what you actually prove when you do a proof. You make sure that this condition holds. Of course, you don't need to do that at the end today, because there are other theorems which tell you that you need to prove something much simpler. I mean, simpler in the sense you need to prove certain statements about entropies, and then everything that leads to the final key with private simplification and error correction, you can use generic results that then tell you this is then guaranteed. But if someone tells you the key is epsilon secure, what he means technically is this. This will be exactly the statement in the standardization papers. So when you open the standardization drafts, that's the statement, I guess. I mean, it's maybe a bit more fine-grained because you distinguish between errors where the two keys are not identical and this independence, but it's basically that.
Why the 1/2 again?
Yes, now let me come to that. So I haven't explained the 1/2 yet. So the 1/2 at this point is, of course, in a sense, arbitrary. So at this point, most things look arbitrary. I could have put here a 3, for example. That's another norm. And I could have put everything into the power of 7 or so. So you see, there are lots of, that's, I think, Uli's point. Mathematically, you can do many nice things. And maybe there are nicer norms mathematically, like the 2 norm is in a sense nicer. It's at least easier to calculate. And so why do I choose this? And the reason for this choice, why is here 1, why is here the 1/2, is that this norm has an operational meaning. And this operational meaning I'm now explaining, and that will also then make clear how we should choose the epsilon. So the operational meaning is the following. So let's now think we have 2 boxes, and these boxes output everything that is relevant, so the K prime and the E. And in order to make my life a bit easier, I will just call these 3 systems together the system X. I can do this, it just stands for everything that is produced. And now I can think of another box which is that, dictated by that behavior, and it also outputs a K prime, and an E. But to distinguish the boxes also formally, I will call everything here together the Y. So this is because I want to talk about both at the same time. That's why I give here different names to the case where I have it produced by the blue box or the red box. So this color now just indicates the probability distribution, if you like. Okay, let's make another simplification, because this is just to illustrate things. I don't want to introduce technical difficulty, which is actually here quite subtle if one does it. So let's assume the E for the moment is also classical, just to understand the concept. So you can think of 3 values output here, the key of Alice, the key of Bob, and the information that the adversary has, which for the moment is classical, and here as well. So now you can think of this as 2 so-called random experiments. One produces a random variable X and one a Y. And what would it mean that these 2 things are actually equal? What it would mean is that the probability distribution of X is equal to the probability distribution of Y. And that's basically now the classical version of saying, if I did it quantum mechanically, this thing here in the red case, this thing red is equal to this thing blue. Okay. Rho K prime E. So this thing with the color code is now reflected by that in the case where I assume E is classical. Now, in the case where I have a distance, I can write it in this context now as Px minus Py is smaller than epsilon. So far I didn't do anything. I just simplified my life by going to the classical case and by summarizing all the stuff that is output by random variables x and y. So now comes the answer. What does this mean operationally? So, operationally, you can think of it in the following way. Assume that you have now, in a sense, two worlds in which, or let's say, this is the thing here I can actually use the ideal thing, functionality in a sense. Let's say this is the ideal thing. This is the stuff that is a perfect key. It's like this, and this is what we actually have. This has potentially errors. Now let's suppose we run this, so we generate keys and we look at what the adversary gets. So we are a referee now. We see everything. So we can collect everything. We can collect the key. We're like a testing unit. We get the device that is sold, but we can also simulate ETH, let's say, and get that. That's of course hypothetical. It would be very hard to simulate all possible ETHs, but let's suppose we could do that. But then we run in parallel, let's say, another scheme which produces things perfectly, which it's just some idealization. So we program a computer to, which locally just generates these things, generates randomness according to uniform distribution and generates some E. And now let's suppose I try to not run them independently, but I run them in such a way that the probability that this x is equal to this y is maximized. So I have now a new, if you want, random experiment where I run both things. So there is an x and a y at the same time. And what I try to maximize is the probability that x is equal to y. That I can do, but my constraint is that so I have now a new situation in which at the same time the real thing runs and the ideal thing runs, but if I only look at this thing, the marginal distribution will be that thing from the red. If I only look at that part, it will be the one from here, but I run them together and I try to make sure they're always identical. Of course, if the distributions are identical, I can make them really always output the same values. So if I have two, like, if I want to, for example, this is a uniform bit and another uniform bit, of course I can make sure I have a new machine that individually, like that, introduces 2 bits. So you have a machine that now introduces an x and a y. If I cover this is a uniform bit. If I cover this, it's a uniform bit. But if I look at both, they're always equal. That I can do if the distributions are equal. But let's suppose, for example, this distribution here is uniform, but this one is not quite uniform. It's 40–60% for 0 and 1s. Then I cannot make sure that this thing is uniform and this not, but they are always the same. They will sometimes deviate from each other. And now what turns out to be the case is that if I try to do that in an optimal way, the probability that the things will be equal will be 1 minus epsilon. So in other words, what I can show is that in principle, if my real scheme works, so this is the thing I really have, I could think of, there would be a shadow world, so to speak, that I don't really see, in which a perfect scheme runs somewhere. It's like a parallel world that runs in parallel. And I know that whatever I see in the real world is actually identical to what happens in the shadow world, except with a probability epsilon. So most cases, my real world is identical, really in value. The values that are output are identical, except with a very small probability. But I also know in this shadow world, everything is perfect. So in other words, I really have now constructed a situation in which the thing I'm designing that I have in the lab is exactly doing the same thing, like a perfect thing, except with a probability epsilon. And now the reason for all the choices, why is there a 1/2, why is it 1 is that we want to prove exactly this, because that has an operational meaning. That's the same as if you buy a car and you want to say an ideal car is one that never breaks down. Now you could say, what does it mean? You can always think when you ride your car that in parallel, if in the shadow world there is the ideal car, and of course what you want is that the real car behaves like the ideal car, but of course there's a small probability the real car breaks down and the ideal car by definition does not. So it cannot always be identical, but you want it to be identical with as high probability as possible. So in that sense, this epsilon can really be understood as a failure probability. And now it's very easy to choose it, because now you can go to an insurance and say that, okay, if a failure, okay, in cryptography, of course, if a failure happens, that doesn't necessarily mean it's a bad failure. It just means it's not behaving exactly as you want it to behave, but potentially it's a very bad failure. Potentially it means the adversary now can empty your bank account or so. So you can now go to an insurance company and say, what this epsilon means if you communicate with QKD, and let's say that's your only source of error, or you have other sources of errors you add there, is how much you can really give a probability of a damage event, or an upper bound at least. And that's what is very common in engineering, and I think you also mentioned nuclear design, where people are very careful. So there people actually give concrete numbers. If you build a nuclear power plant, you have to give a number. You have to say, what's the probability that this thing, that there's no core melt? And for example, you can look up in the standardization for nuclear power plants, and there the specification is that in Germany, and this is the old specification, don't be worried, that the core melt should not happen with a probability larger than 10⁻⁵ per year, which is actually a very large value, because it means if it operated 50 years, then it's already of the order of 10⁻⁵. And so if you have 1,000 power plants, it means it's very likely one of them will have a core melt, which is actually what happened in the real world. If you count the number of power. So it's a bit worrying value, but it was actually not that wrong. But now, you see, we can really be very concrete. You can now say, okay, you have a crypto system. The damage, if it happens, it's not that expensive, so we can tolerate a probability of error that is, I mean, if you have a power plant next door, there's no point in choosing an epsilon which is smaller than the one of the power plant, because if the power plant explodes, your QKD scheme will anyway. So, in a sense, this gives you really a feeling of how to choose the value. So it has a very concrete meaning. It's really the failure probability. And of course, it depends on your application. Now, what is important to realize, this is the last thing I want to say, is like in the power plant example, I had to say, what's the failure per year? And you have to specify what's the epsilon per what is it. And for example, in a QKD scheme, you usually run it once and you get a key of 1 million bits. So you have kind of instance where you press a button. And so you need to specify the epsilons, for example, per use of the crypto system. Then you have to, of course, to be careful if you define it for very small block sizes and use it 1 million times per day, then you may want the epsilon to be smaller because these add up. So each time you use it, you have a failure probability of epsilon. So if you use it 1 million times per day and you want to make sure during the whole day there is no failure, you have to make sure that 1 million times the epsilon is still a small value. So that's something to keep in mind. Okay, I think now you know what we want to achieve. So that's the security definition. And in the next lecture in the afternoon, we will go through the steps to actually achieve this. But before doing that, I will, as I promised, talk about the assumptions that enter QKD, because we need to make sure we can use certain ingredients here in these proofs, and we need to specify them explicitly. Okay, I think it's time for lunch.